A C program talks to the computer using a few basic containers called fundamental data types. They are mostly predefined by the implementation, but on a typical 32-bit or 64-bit PC you get. Char occupies 1 byte 8 bits. When declared as signed char, the binary pattern is interpreted using 2's complement, giving a range of -128 to +127. As unsigned char, every pattern is a non-negative value, so the range becomes 0 to 255. Example, the number 65 is stored as binary pattern for the ASCII code A. Int. Most modern compilers make int 4 bytes 32 bits. Signed int uses 2's complement, so the smallest value is -2,147,480,3,648, and the largest is +2,147,480,3,647. Unsigned int runs from 0 to 4,294,967,295. You can see the limits in limits.h as int min, int max, uint max. Float 4-byte IEEE 754 single precision. It stores a sign bit and 8-bit exponent bias, 127 and 23 bits of mantissa. The format can represent roughly 7 decimal digits accurately. For example, the decimal 3.14 is stored as hexadecimal 4048F5C3, which is binary 0.10000000001010101010101011. The smallest positive normal value is about 1.175 times 10 to the -38, and the largest finite value is about 3.402 times 10 to the -38. Double 8-byte IEEE 754 double precision. It has a 1-bit sign and 11-bit exponent bias 1023 and 52 bits of mantissa, giving about 15 to 16 decimal digits of precision. The range is roughly 2.225 times 10 to the -308 to 1.797 times 10 to the 308. These sizes and ranges are implementation defined. The C standard only guarantees minimum ranges. For example, char bit is at least 8. Understanding the binary layout helps you see why overflow can happen and why some values cannot be represented exactly. For example, 0.1 in binary is a repeating fraction. Derived types are built from the fundamentals to model more complex data. Into open bracket 5 close bracket reserves 5 times 4 equals 20 bytes, laid out exactly as a open bracket 0 close bracket, a open bracket 1 close bracket, a open bracket 4 close bracket in memory. The address of A is the address of its first element, so pointer arithmetic works. A +2 points to a open bracket 2 close bracket. Int star p semicolon occupies typically 8 bytes on a 64-bit machine. The value of p is the address where an int resides. Star p dereferences that address. Because a pointer is just a number, you can cast it to other pointer types, but the compiler must be told what type you intend. Structures pronounce struct group different types into a single record. Example, struct point open brace int x semicolon comment 4 bytes, int y semicolon comment 4 bytes, char tag semicolon comment 1 byte, close brace semicolon. Most compilers align each member to its natural alignment, usually its size. After y comes a 3-byte padding, so that tag starts at an address that is a multiple of 4, and the whole struct may end with another 3-byte padding to make its total size a multiple of 4. Sizeof struct point often becomes 12 bytes, not 9. Unions share the same storage for all members. All members start at the same address. The size of the union is the size of its largest member plus any padding needed for alignment. Example, union data open brace int I semicolon comment 4 bytes, double d semicolon comment 8 bytes, char c open bracket 8 close bracket semicolon comment 8 bytes, close brace semicolon. Sizeof union data is 8 because the double or the char array are the biggest. Enumerations pronounced enum assign integer constants to names. By default, the underlying type is int, so enum color open brace red comma green equals 5 comma blue close brace yields red equals 0, green equals 5, blue equals 6. The compiler stores the enum value as a 4-byte int, but you can force a different size with enum attribute packed, non-standard, or by using typedef enum open brace, close brace color semicolon and casting. These derived types let you model real-world objects. An array is a row of seats, a pointer is a road sign pointing to a house. A struct is a passport that bundles name, age, and nationality, while a union is a Swiss Army knife where only one tool can be used at a time. Explanation: type qualifiers modify how the raw bits of a type are interpreted. Signed/unsigned. The same bit pattern can be read as a sign 2's complement number or as a non-negative integer. Adding the qualifier changes the range and the result of arithmetic. Example: unsigned char UC equals 250, UC plus 10 yields 4 wraparound modulo 256. While signed char SC equals 250, which is actually minus 6, and SC plus 10 yields 4 as well, but the intermediate value is different. Short/long, these change the size of integer types. Short int is at least 16 bits, long int is at least 32 bits, and on many 64-bit systems long int is 64 bits. The qualifier can be combined with signed or unsigned, for example unsigned long. Const tells the compiler that the object will never be modified after initialization. The compiler can place a const object in read-only memory and will emit an error if you try to assign to it. Example: const double pi equals 3.14159 protects pi from accidental changes. Volatile warns the compiler that the value can change at any time outside the program's control. For example, hardware registers, signal handlers, or variables shared with another thread. The optimizer must therefore generate a fresh load each time the variable is used. Example: volatile int pointer port equals cast to int pointer address 400210000 ensures the compiler does not cache the value of the I/O port. Together, these qualifiers let you express intent and enable the compiler to generate safer, more efficient code. Think of const as a do not touch sign on a jar, and volatile as a jar that is shaken by someone else while you are looking at it. Storage class specifiers control three aspects of a variable: scope, which is where the name is visible; linkage, which is whether the name can be referred to from other translation units; and lifetime, which is how long the storage exists. Auto is the default for local variables inside a block. Its scope is the block, its lifetime starts when the block is entered and ends when it is left. Example: void f of void open brace auto int counter equals 0, comment same as int counter equals 0, counter plus plus, close brace. Register hints to the compiler that the variable will be used frequently, so it would be beneficial to keep it in a CPU register. You cannot take the address of a register variable. Ampersand counter is illegal. Modern compilers often ignore the hint and decide on their own. Static has two different meanings. Inside a function, static makes the variable retain its value between calls. Its lifetime is the whole program run, but its scope remains the function block. At file scope, static gives the variable internal linkage, meaning it is visible only inside that translation unit source file. It also has static storage duration, allocated once for the whole program. Void g of void open brace static int calls equals 0. Comment keeps count across calls, increment calls, close brace. Static int module counter equals 0. Comment visible only in this file. Extern declares a variable that is defined in another translation unit. It gives the identifier external linkage so other files can refer to it. The definition must exist exactly once somewhere. Extern int global value, comment declaration, no storage allocated here. Default behaviors. A file-level variable without any specifier is extern with static storage duration. A block-level variable without specifier is auto. These rules let you control memory usage, automatic versus static, visibility across files, and sometimes performance register. Imagine a room function where auto variables are temporary guests that leave when the room closes, while static guests stay forever, and extern guests live in another house but can be invited in. When a C program starts, the operating system creates several distinct memory regions. Each region has a purpose. Code text segment holds the compiled machine instructions. It is usually marked read-only and executable. All functions live here. Data segment initialize stores global and static variables that have an explicit initializer. Example: int g equals 5 resides. BSS segment block started by symbol holds global/static variables that are not explicitly initialized, which the loader automatically zeros. Example: int counter. No initializer ends up in BSS. Heap grows upward toward higher addresses and is managed at runtime by malloc-free. New etc. memory is allocated in variable size blocks and persists until you explicitly release it. Stack grows downward toward lower addresses and stores function call frames. Local auto variables return addresses and saved registers. Each call pushes a new frame, returning pops it. Visually, a typical 64-bit process layout, low address to high address, might look like text segment, data segment, BSS segment, heap stack. Understanding this layout helps you reason about where variables live, why stack overflow occurs, and how memory leaks happen when heap blocks are never freed. C performs implicit type conversions in many expressions, following a well-defined set of rules called the usual arithmetic conversions. Integer promotions. Small integer types char, short, bool are first promoted to int or unsigned int if they cannot represent all values of int. This means that in most arithmetic, a char behaves as a 32-bit int. Usual arithmetic conversions. When two operands have different types, the compiler converts the one with the lower rank to the type with the higher rank, according to these steps. If either operand is long double, the other is converted to long double. Otherwise, if either is double, the other is converted to double. Otherwise, if either is float, the other is converted to float. Otherwise, if either is unsigned long, convert the other to that type. Otherwise, if one is long and the other is unsigned, follow specific rules. The net effect is that mixed type expressions are evaluated in the widest type. Int I equals -5, 2's complement representation Xerox FFFFFFB. Unsigned U equals 10U, int result equals I plus U is unsigned, so I is converted to unsigned. I becomes 4,294,967,291 unsigned. Result becomes 4,294,967,301. Unsigned, modulo 2 to the 32 equals 5 unsigned. The addition yields 5 as an unsigned value, which is then assigned to a signed int. The conversion back may produce implementation defined or undefined results if the value does not fit. Float f equals 1.5 f, double d equals 2.5, auto x equals f plus d. F is promoted to double, result type is double 4.0. Explicit casting lets you override the implicit rules. Int a equals cast to int of 3.9, truncates to 3. Double b equals cast to double of a divided by 2, 3.0 divided by 2 equals 1.5. Casting should be used carefully. An ill-placed cast can hide bugs, such as casting a large unsigned to int and losing high bits. Explanation: the size of operator yields the size in bytes of its operand after all type adjustments including padding. It is evaluated at compile time for most objects. Alignment is the requirement that an object's address be a multiple of a certain power of 2, typically its natural size. Compilers insert padding to satisfy alignment, which can make a structure larger than the sum of its members. Struct example: open brace char c semicolon comment 1 byte alignment, 1 int I semicolon comment, 4 bytes alignment, 4 short s semicolon comment, 2 bytes alignment, 2 close brace semicolon. C starts at offset 0. To align I to a 4-byte boundary, the compiler adds 3 bytes of padding after C, so I is at offset 4. S wants a 2-byte boundary. After I at offset 8, there is no need for extra padding, so S is at offset 8. The total size becomes 10 bytes, but the compiler may add trailing padding so that the size is a multiple of the strictest alignment, 4 bytes. Hence size of struct example is usually 12. Print open parenthesis double quote size %zoo comma space, offset C %zoo comma space I %zoo comma space S %zoo backslash, n double quote close parenthesis, comma new line size of struct example, comma offset of struct example, comma C comma offset of struct example, comma I comma offset of struct example, comma S close parenthesis semicolon. The output confirms the padding. Why it matters: when you map a structure onto hardware registers or a packed file format, unwanted padding can break the layout. Compilers provide pragma pack or attribute packed (GCC) to suppress padding, but using them may lead to slower accesses on architectures that require alignment. Understanding size of and alignment helps you write memory-efficient code and avoid subtle bugs caused by misaligned accesses. Integer overflow. Signed overflow, for example, int a equals int max, a equals a +1, invokes undefined behavior according to the C standard. The compiler is free to assume overflow never happens, which can lead to surprising optimizations such as removing the addition entirely. Unsigned overflow is well defined and performed modulo 2 to the n, where n is the number of bits. Example: unsigned char uck equals 250, uck equals uck plus 10 yields 4. For an n-bit unsigned type, the result of x plus y is x plus y modulo 2 to the n. Floating point precision. Floating point numbers follow the IEEE 754 format, which can only represent a finite set of rational numbers. Many decimal fractions become repeating binary fractions, causing rounding errors. Classic example: double A equals 0.1, double B equals 0.2, double C equals a plus B, expected 0.3, print C with format percent. 17G, print 0.300000000000000004. The tiny error arises because 0.1 and 0.2 cannot be represented exactly. They are stored as the nearest binary approximations. Consequences: direct equality comparison, C equals 0.3 may fail. Accumulating many small errors can lead to noticeable drift, for example, summing 1/3 a million times. Safe practice: compare floating values within a tolerance. For example, absolute value of C minus 0.3 less than 1 times 10 to the minus 9. Combined pitfalls. Consider mixing signed overflow with floating conversion. Int I equals int max, which is 2147483647. Float f equals cast to float I, may lose precision, becomes 2.147483659. Int j equals I plus 1, undefined behavior. Float g equals cast to float j, undefined result. Because the intermediate integer overflow is undefined, the subsequent cast to float can produce any value. Understanding these rules protects you from subtle bugs that appear only under extreme inputs or specific compiler optimizations. Question: what is the default storage class for a variable declared inside a function without any specifier? Answer: auto. The variable has block scope, automatic storage duration, and no linkage. It is created each time the block is entered and destroyed on exit. Question: how does static differ when used inside a function versus at file scope? Answer: inside a function, static gives the variable static storage duration, exists for the whole program, but block scope, visible only inside that function. At file scope, static gives the object internal linkage, visible only within the translation unit, while also having static storage duration. Question: which storage class allows a variable to be kept in a CPU register, and why can't you take its address? Answer: register. The compiler may place the variable in a register for faster access. Because a register does not have a memory address accessible by the program, the language forbids the ampersand operator on a register variable. Question: identify the segment where the following variable resides. Int global equals 42. Answer: data segment initialized because it is a global variable with an explicit initializer. Question: what happens to an uninitialized global variable like int counter? Answer: it is placed in the BSS segment and the loader 0 initializes it before main starts. Question: explain why size of struct open brace char c. Int I, close brace may be larger than size of char plus size of int. Answer: the compiler inserts padding to align int I on a 4-byte boundary and may also add trailing padding so the whole struct size is a multiple of the strictest alignment. This prevents misaligned accesses on many CPUs. Question: what is the result of unsigned int u equals unsigned int max? U equals u plus 1, and why? Answer: the result is 0. Unsigned overflow wraps around modulo 2 to the 32 as defined by the C standard. Question: is signed integer overflow defined? Provide an example of its undefined nature. Answer: no, it is undefined behavior. Example: int I equals integer max, I equals I plus 1, may produce any result, cause a trap, or be optimized away by the compiler. Question: when should volatile be used? Answer: for objects that can change outside the program's control, such as memory-mapped hardware registers, variables modified by an interrupt service routine, or variables accessed by multiple threads without synchronization. Best practice pitfalls. Forgetting static on a function local counter leads to it resetting on each call. Using register and then taking its address triggers a compile time error. Assuming signed overflow wraps like unsigned can cause subtle bugs and non-portable code. Omitting const on parameters that should not be modified reduces readability and may prevent the compiler from optimizing. Ignoring padding when interfacing with external binary formats results in misaligned data structures.